Aufnahme starten. Stream starten. Right. Yes. Go. Good afternoon, everybody. Welcome you to SCI33205 M604, right? 3205 M604, which is physics number 4, right? ทำไมมันเลื่อนหน้าช้าอย่างนี้ Okay, we are here at the เดี๋ยว capture ไว้ก่อนนะครับที่ YouTube. We are here at the topic of Lenz's law, right? In order to find the direction of the induced electromotive force, right? Right there in yeah. If you have the permanent magnet right like this here, okay, and if you want what if you want to see some effects from this one, right? This good note. If you want to see some effect how the current will appear in this copper conductor, right? The circular loop. If you have N pole, right? This is the north pole of the permanent magnet. And you point the north pole to the circular loop of the conductor, and you put it, okay, you move it into the face of the circular loop, right? And you would find that there will be magnetic flux difference, right? Before that, the conductor can realize only a little amount of the magnetic flux, right, which is at T1, right, 5B1, and when you move it to be closer to the conductor will realize, okay, will perceive or will feel that the magnetic field is stronger. Okay, that's why they say the longer vector. And with these two states, with the comparison of both situations, we find that there will be change in magnetic flux, okay, which is denoted by delta phi b. Okay, delta phi b is something important to this scenario, all right, because the EMF will emerge due to the quantity of flux change. Yeah, or there is flux change in this direction, and Lenz found that there will be the conductor doesn't like that situation. Okay, he tries to keep the amount of the magnetic flux, okay, to be the same as the first situation, which is 5B1. So in order to do that, okay, you just measure the length. Okay, the conductor will measure the length of this vector, the flux chain, and he make the same amounts of flux chain to make the magnetic flux. Okay, and then the direction of the induced magnetic field is opposite to the chain in flux or flux chain. Okay, this is be induced, and that's what happened. And in order to be induced, okay, the conductor should behave itself, okay, by generating a current, okay, a current rotating in this circular conductor. And yeah, the direction here should follow the right hand rule. Okay, you leave yourมีเปิดไมค์ด้วยนะครับ the thumb direction points same as the direction of the B induced, okay, and your remaining four fingers will represent the direction of the current rotating in this circular loop, okay. And that's the first situation, okay. It's straightforward. You just move the north pole to the circular conductor. In the opposite way, if you move the south pole, okay, on the other hand, if you move the south pole into the conductor, what is going on, okay, let's make an analysis in the following. You move the south pole, right, in but from what we have heard at the beginning of this chapter, the north pole is the place that generates the magnetic field lines, right? But the south pole is the place where the permanent magnet receive, right, or get the magnetic field lines. So you can see all the arrows of the magnetic field lines pointing to the south pole of that permanent magnet, okay. And yeah, of course, the conductor is the main object for us, right? It's the main interest for us. He realized that there is magnetic field lines in this direction, okay, in the upward direction, in the vertical direction, like this, okay, in the up direction. And when you move it, when you move the permanent magnet to be closer to the circular conductor, you will find that at the state 1, okay, the flux vector phi b1 is has the height like this, okay, is of the height like this. And when you move it closer, this vector is going to be stronger, which means it has a longer magnitude, okay, which is phi b2. And you could find the difference between these two states, right? Two states. And yeah, it's called again the flux change, okay, delta phi b. Yeah, but the conductor is the lazy guy, okay? He's a lazy person. He doesn't like this behavior when someone change the environment around him. So he tried to compensate the additional vector of the flux in this direction, okay, by making himself, okay, the magnetic field, okay, in the opposite direction, but with the same magnitude, with the same length of this vector. มีใครเข้ามาอีกไหมครับไม่มีแล้วนะโอเคผมพะวงเดี๋ยวผมลืมไม่กดรับคุณนะครับโอเคสุภสินกิติพันธ์มาครับขออนุญาตแคปเจอร์ที่ YouTube ไว้หน่อยนะครับyeah, the induced magnetic flux is gonna point in the opposite way again, okay. This one again is pointing in the opposite way, okay, to the flux change vector. And here again, but the flux change vector is pointing upward, okay, which is opposite to this situation on the left side. The B induced will follow the same, okay. It will have the opposite direction to the flux change vector, okay. Now it's going to point downward. In yeah, in order to get the B induced, the magnetic field the induced magnetic field pointing downward like this, you have to lay down your right hand, okay, your thumb direction along the direction of the induced magnetic flux or vector B, and you will find that your remaining four fingers is gonna represent the current that should flow in this circular conductor, okay. And yeah, your four fingers would give the direction of the current flowing in the circular conductor like this, okay, that's the conventional from the right hand rule. Okay, that's the first situation. You move both permanent magnets, whether it's with the head of north pole, with the head of south pole toward, okay, the circular conductor. But let's consider the different situation if you move it out of the circular conductor. For example, okay, let's consider first the conventional way we leave the north pole toward the conductor, but now we don't move it we don't move it to จริงๆ605จะเข้ามาเรียนพร้อมกันเลยก็ได้นะแต่ว่าเอาไม่เป็นไรเอาตามตารางเดิมก็ได้นะครับเดี๋ยวจะหาว่าผมขี้เกียจสอนอยากสอนรอบเดียวif you let's consider the conventional way first. Okay, the north pole pointing to the circular conductor, but now we don't move it toward the conductor. We move it out of the conductor, and we would find that before the flux has the vector, okay, pointing downward, right? And when you move it out of the conductor, the magnetic flux is gonna be lighter, right? It's gonna have less impact to the conductor, right? Here, at the first state, you have 5B1, okay, magnetic flux with quite long, okay, long vector, and after that, you move it out of, okay, the conductor, and you get lighter amounts, okay, or smaller amounts of the magnetic field or magnetic flux, okay, that's represented by the shorter vector here, 5B2. We make the difference in physics, right? The final state minus the initial state, right? So we get the delta phi b, which is the difference of the flux change, or the difference of flux, okay, between those situations, and we find that the flux change, okay, vector is pointing upward like this. Okay, it has lighter amount of magnetic field, right? So the flux change is pointing upward like this, and the conductor is the lazy person. Okay, he doesn't like that situation when someone disturb him. He tried to compensate or to remove or get rid of this flux change, so he has to generate by himself the magnetic field, okay, in the opposite direction to this one again. Okay, this is upward, so he generates the magnetic flux in the downward direction, okay, with the same length, okay, with the same magnitude as the flux change. But now let's consider if he wants to generate the induced magnetic flux with the downward direction like this, okay, he has to use his right hand, okay, and this is the thumb direction. His remaining forefinger is gonna give us the direction like this, okay. And that's the first case. The third case, okay, when we move the north pole out of the conductor. Now let's consider the situation when we move the south pole of the permanent magnets out of the conductor. Okay, before that, we get quite strong magnetic field lines with the upward direction, and when we move the permanent magnet out of this conductor, we're gonna get lighter magnetic field, right? Or the smaller amount of magnetic field lines. So at state 1, we get the strong, okay, flux, which is 5B1, and at the second situation, we move the permanent magnet out of the conductor, we get lighter magnetic flux, which is 5B2. Okay, that's why we can see here the shorter vector. And in physics, we have to measure the difference, right? The final state minus the initial state, okay, 5B2 minus 5B1. we can observe that there is reduction of the magnetic flux, so we get delta phi b, okay, vector, and its direction is directed. Its direction is downward, right? Like this. In the conductor doesn't like this situation. Again, he tried to create or compensate the additional shape, the additional magnetic flux. Okay, here we have the downward magnetic field, so he has to generate the upward magnetic field, and he laid out again his time direction in the same way as the magnetic flux that has to be induced. Okay, and his four fingers will represent the current that will happen in this circular loop. Okay, and that's all. Those are all four cases that we can use and we can observe. Okay, whether it's moving into the is moving toward the conductor, is moving out of the conductor. It doesn't matter, and that's those four figure or situation are taken from one book, and here is another situation. If we take it, if we consider it from another book, right? Here we have the currents flowing upward like this, and from the ampere law or the right ampere just use the right hand rule, right? So the induced, it's quite related to the BO Sawat. Okay, if you want to find the strength of the induced magnetic field, you just you just use your right hand, your thumb direction laying down according to the direction of the current. Your remaining four fingers will represent the magnetic field, right? Magnetic field lines, which has the circular shape like this. And because these conductor that's like, okay, he has to before that, if we don't let the current flow, okay, there will be no magnetic field, the green one here, okay, magnetic field lines, the green one. But when we let the current flow upwards, as in the okay, if we let the current flow upwards, okay, according to the figure, okay, as in the figure, we get the magnetic field lines like this, and this is the conductor, another conductor which is around, has a closest loop, right? Whether it's rectangle or circle, okay, whether it has the rectangular shape or a circular shape, okay, doesn't matter. The important thing is that we have the closed loop of the conductor. Yeah, and that's what we could expect. ผมไปโดนเมาส์อะไรเขา Yeah, that's what we could expect again. Okay, even it's different situation. We don't have permanent magnet, but we just use the principle of the induced current. Okay, this conductor, that's like the situation when someone disturb him, okay, by putting the magnetic field into his internal area here, okay, his area. So he tried to compensate or to get rid of the additional magnetic field by generating the magnetic field with the same amount but in the opposite direction. You can see here, this is the generated magnetic field, and in order to have the magnetic field to compensate or get rid of the someone disturbing him, he has to make the current, okay, and he has to generate the current, and the current direction should follow or satisfy this magnetic field. Okay, again, you use the right hand, and your forefinger will represent the magnetic field lines here, okay, the induced one, and your thumb direction is gonna give you direction of the induced current. Okay, here is the Lenz's law. Okay, it's quite close to the the Faraday's law. Faraday's law will give you the quantity, okay, how much you could get the electromagnetic force, okay, which is simply known as voltage. All right, here we have another type, okay, which is quite related to the former four figures, four previous cases. We have again permanent magnet and the circular coil, and yeah, we move the permanent magnet. Okay, that's the conventional way, right? The south pole of the permanent magnet or any magnet will be the place where magnetic field line is gonna get into, right? And at the north pole side, we have the place. We have the source, right? The source that generates or let the magnetic field lines get out of. Okay, yeah, getting out of, and we move this permanent magnet toward the current to the circular coil, and of course, this guy, the conductor, doesn't like that moment. Okay, when someone tries to disturb him, okay, he tries to act against this increased amount of the magnetic field. Okay, in order to get rid of the additional amounts of the magnetic field, he has to generate the magnetic field in the opposite way again. And in order to get the magnetic field in the opposite way, he has to use the right hand. Okay, your thumb direction pointing into the magnetic permanent magnet, and your four fingers will represent the induced current, and then you get the current flowing, turning around like this. All right, and yeah, here is the figure that explains how or the mechanism of generating the magnetic field to be against the additional the increasing amount of magnetic field stemming from the movement of the permanent magnet. Here, in order to have the magnetic field like this, okay, from right to left, we laid out our thumb, okay, according to direction of the magnetic field. We have the four fingers which represents the direction of the induced currents, the I vector here. All right, yeah, you can see that this is the place we can consider as the North Pole. Okay, North Pole is the place that generates the magnetic field lines, right? And we can see on the right side that here we have the South Pole. Okay, because this is the place where the magnetic field lines are getting into. Okay, yeah. Something else. You can have again the same situation even you don't use the permanent magnet. If you use the something different but it has the same property, it's called electromagnet. Okay, it's not permanent magnet. Both are magnets. Okay, the object that generate the magnetic field, but permanent magnet has nothing to do with modification. It just simply deliver the magnetic flux, okay, without any modification, without any effort. But electromagnet is the object that can generate the magnetic flux in the same way as the permanent magnet, but we can control the generation of the magnetic flux, okay, by turning on, switch on the current, okay, or switch off, okay. If you let the current flow like this, okay, and yeah, you will find that the magnetic field is gonna point into this direction, right? If you use your right hand and your forefinger represents the current movement, okay, which is the direction turning around like this, and your thumb direction is gonna be the direction of the magnetic flux, okay, which points to the left, right? Okay, and when you didn't switch it, nothing happened. The coil realized that there is no magnetic flux at all across my surface. But when you switch or turn the switch off, okay, now there is current movement, and the magnetic field will start to flow or go in this direction. And the conductor will realize that someone disturbed me. Okay, he let the magnetic field passing through my area like this, from right to left. He doesn't like that situation. He tried to get rid of the increasing amount of the magnetic field. Okay, before that, at the first stage, he doesn't have magnetic field light all across his surface, but in the second situation, someone disturbed him. Okay, in order to get rid of the increasing amount of magnetic field, he has to generate the magnetic flux in the opposite way. Okay, in the opposite way to the direction of someone putting or placing the magnetic field to him. Okay, so the direction that acts against this one, okay, should be the one that directed from left to right. Okay, from left to right, that's the decided direction for the magnetic field that this conductor, the I don't know, it's green or no, it's orange or I don't know here. Yeah, this conductor should generate the current in order to have the magnetic field from left to right sides, and here he generate the current. Okay, thumb direction represent the magnetic field which points from left to right, and remaining four fingers will represent the induced current, which is this one. Okay, I hope that you completely understand. Okay, now we will solve. We will have an example to our situation regarding the Lenz's law and so on. Here we 14 20นะ14ผมต้องปล่อยคุณใช่ไหมครับโอเคนะ20นาทีชวินมาครับโอเค all right, here this is taken from the book number 1, example 21.2 in figures 78. This is a special device, okay, or special apparatus in the laboratory. We have permanent magnets, okay, the North Pole, the South Pole, and of course the North Pole will generate is the place where the magnetic field line start, right, and it's gonna end or reach the South Pole. Okay, and assume that all of magnetic field lines are pointing straight. Okay, there is no curvy movement. Okay, only straight line direction for the magnetic field lines. Okay, and this is the spatial device. He has also the owner of this figure has also the conductor, right? The copper wire, which has circular shape. Okay, approximately circular shape, and at the end of the circular conductor is we connect the voltmeter, I don't know, voltmeter or ammeter to this conductor, right? And they say the area, the cross-sectional area of this conductor loop, whether it's ellipse, whether it's circle or any kind of shape, okay, of the conductor, but let's say it has the area of 120 square centimeter, or if we convert it to the square meter, it's going to be this number divided by 10,000, right? So it's going to remain 0.012 square meter. And this conductor is not perfect, okay? It's not superconductor, which operates in very, very negative temperature. Okay, it has its own internal resistance. Okay, because it's not perfect metal, and assume that from one side to another end we have 5 ohm for the resistance of this conductor. And now let's take a look at the question in this one. Yeah, that device has a uniform magnetic but okay, it's uniform across all the area in that device. Okay, the amount, the density of magnetic field lines here are considered or assumed to be the same. Okay, there is no place where the magnetic flux is denser than the other area. Okay, everywhere here has the same density for the magnetic field line. And assume that if someone can control this permanent magnet, the magnetic field changes. They don't say from what value to what value, right? So they just say that there is a change of the magnetic flux per time as 0.02 Tesla per second. Okay, in 1 second, the magnetic field line is higher by 0.02 Tesla. Okay, in 1 second. And what else? The area cross-section area 120 square meter. Okay, the internal resistance of that conductor is 5 ohm. Okay, find the magnitude of the induced EMF and the induced currents in the circuit. So we have to talk about the Faraday's law, right? We have Faraday's law as this one, right? And yeah, it's epsilon is band, right? Band omega, right? Band omega is that's the for the generator. This is Faraday loss is minus n and delta phi b by delta t, right? And phi b is this one. Okay, if you want to see the expression of phi b from the beginning of this chapter, be a cos phi, right? Yeah, phi is the angle between the normal vector of that conductor to the magnetic field direction, right? Vector B and vector A. Okay, dot product between vector B and vector A. Okay, that's why we get cosine. Yeah, we are gonna use that formula in order to solve this one, right? So let's start to do that. It's better we use this one. Okay. All right. How to do that? They asked us about the magnitude of the induced EMF, right? So we have to consider the formula by Faraday, okay, which is epsilon equals minus n and delta phi, right, by delta t, right there. Okay, this formula delta phi by delta t. All right, and but they didn't ask us about the actual value for the induced EMF, but rather they asked us the magnitude of the induced. Okay, magnitude. So we should take the absolute value to this expression. So we're gonna have the absolute of epsilon is equal to absolute of minus n, right? In and delta phi divided by delta t and the absolute value like this, right? In yeah, the absolute value will be distributed to both quantity, right? So it's going to be this one, right? The absolute value of that one and the absolute value of delta phi b actually. Okay, phi b divided by delta t right here. Yeah. Yeah, this one. We will remove the negative psi, okay, because it doesn't certify the absolute value, okay. So we take only the positive value for that. So it's gonna be n and the absolute value of delta phi b, right? So he said that there is flux change, but it's not possible. This is delta b per time, right? So we have to consider the delta phi b, right? Phi b is b a cosine phi, right? Phi is the angle between the normal vector of that area to the magnetic flux direction, right? So delta phi b is, in this case, we would see that in this one, the area doesn't change with time, right? Because we didn't increase the size of the connector at all, and there is no rotation of this conductor, so the phi will be the same, right? So there is no change in angle, and you can see that here the direction here, right? This is the normal vector, and the green one is the normal vector for the area of this conductor. The blue one is the magnetic field direction, right? The b vector and the n vector. So the angle between these two vectors is 0 degree, right? So we can substitute 0 to this one, and cosine of 0 is gonna be 1, right? And b change with time, but the area doesn't change. So we would have delta phi b is gonna be a times delta b, right? Okay, delta phi b will be a delta b. So we will substitute it into this one. All right, a and delta b, right, in divided by delta t, right? And yeah, because the area will never be negative, okay? Have you ever heard any area to be negative? Okay, usually the area is positive. We can move it out of the absolute symbol. So we would have right now n and a, right? And what we get here is delta b by delta t, and the question in this example says that delta b and delta t is 0.02 Tesla. So we will substitute. Okay, from the figure, even they didn't say how many turns of the coil. You can see here that there is only a single turn for the coil, right? So it's gonna be single turn, okay? N number 1, n is equal to number 1, okay? One turn. And a is the area of this conductor. Okay, we don't know whether it's circle or rectangle. Okay, they didn't say the detail. So we will substitute 0.012 to the variable a 0.012 and square meter, and delta b by delta t is what they have already provided here, which is 0.02. Okay, 0. You can also leave the absolute value, but it doesn't matter at all. Okay, 0.02 Tesla per second, right? And closing. Okay, like this. And yeah, we leave it. We move. We place all these three amounts into the calculator. Okay, we get the multiplication result. Okay, what is that? ครับอะไรกันอะไรอ่ะ12 2ใช่ไหม12 2 24 okay 24 right in 24 it's equal to 0.00024, right? So 5 position, the 5th position after the decimal point, and we get that in the unit for the epsilon is the volts, right? And if you want to represent it better in the better way, we would say 24 times